you'll get to see that. These things, if you take the actual class, you'll get to see it in depth. So I'm not really worried. So what is the soup? I know you ask that question all the time. So first you need a definition of bounded. And you know what's great? I've already ruined you. I think someone asked me, I put the word bounded in something, and somebody asked me in class the other day, what does bounded mean? You haven't defined it. So you have to demand that. All right, if you have a subset of real numbers, you say it's bounded. If there is a B, a set B and R, so not a set, a point B and R, and a little b and R, with the property that X is stuck between that capital B and little b for all X in A. And we say that A is a bounded set. So it's exactly what you think it should mean, that there's an upper limit and there's a lower limit on the stuff that's in the box A. Why don't we do the portfolio pickups also on Friday? So revisions, which you have very little to do, I think, and then the portfolio, organize that thing, shape it back up. So you use this definition just like any other. If you're given, if your know is that you have a bounded set, then you pull this out and say, then I know there exists a capital B and a little b such that all x's in the set are between that little b and capital B. I'm going to put some stuff up on Excel for you so you can see some of things, but let's see, does everybody have it down? So for example, if I have a sequence as a set, you can think of the y values of the sequence being the set, which we write, that's a bounded sequence. Why is that? Well, if I take B equals, capital B equals 2, that's an upper bound. Every single element in A is capped above by 2. For sure. And minus 1 is a lower bound. I'll move this over to the side and then we'll put it back in here. I didn't like that. This is how I graph. I'm going to give you an in-class assignment where I ask you to do things in Excel. Don't tell Colonel Clark. You can do it in Python or if you want to. Colonel Scaletti and I believe that some things are just easy in Excel. Just do it in Excel. We keep that a little bit to ourselves. So let's say n equals 1. So if you have, if you want to plot a sequence, you can think of the n's as being the x's and the an's as being the y's. So if I plotted that in Excel, some of you had 103, so they actually taught you how to use Excel in there. You can put an would be 1 over n, so n is in the a column, so you put 1 divided by a2. And that gives you an. And then over here, you want that to scroll up without having you tell it to scroll up. So that's a2 plus 1. And you can see that gives me a2. And then I just float this down. How that works is you highlight the cells, go up, makes a tiny little cross, and then you drag down, and it drags your formula down. And so then you can see a plot of what you're drawing. See what that looks like. I'm not going to make this look nice, but you know, you can make it look nice if you want to. You can go down to here, quick layout. I'm writing a paper now where I just gave up trying to do it in R, and I put them in nice Excel figures because at some point it's hard to go back and forth with R over and over. It just is more work intensive. So I just want to see the picture. So I got a pretty decent looking thing. And I can see that if I think of those sequence members as playing limbo, and there's a bar that's on top. If I put the bar up at 2, y equals 2, it's all those sequence members are under y equals 2. And if I put a bar down at -1, everything's above -1. It's like a limbo bar above and a limbo bar below that you have to jump over at the same time. That's a good game.
It doesn't, like, your upper and lower bounds don't have to be the closest bounds, though.
We're getting to that. Watch as the drama unfolds. You're getting there. So, and upper bound, there could be lots of upper bounds. So, can you find better ones? Let's go back and look at that picture. What's the best upper bound? 1. So I can put a line right at 1. In fact, I can do that because I can. I can do insert. Where's my shapes? Usually I have a shape one. Well, I can do that, right? I can just, like, that's my line. There's 1. And I could do this, 0. There's my best limbo bars. 0 doesn't have to be in the set. So it's not a min. The definition of minimum is it's in the set. So there's a difference between minimum and this lower bar. And there's a difference between maximum. It turns out that the max and the best bar on top are the same because the maxes and mins have to be inside the set. You might want to jot that down. I don't have it in the notes. If I say it's a minimum, so in 476 actually, the book is very interesting. It's a great book because it's the only book I think that's out there where they step around these little issues that would freak out someone in analysis. I like the book because I was never freaked out. Sometimes there's books that try to pitch it at an undergraduate level and you get freaked out, like you don't really have the right definition here. But they step around all that by not talking about maxes and mins at all. And they only mention a min or a max if it's inside the set. But the maxes and mins have to be inside the set by definition. But 0 is kind of like a min. It's kind of like it. It's just not inside the set. So we designate that best bound as being called, the top best bound is called the supremum, or the sup for short. You can call the sup the supremum if you want to. He'll probably like that. And 0 is called the infimum, or the inf. That would be the lowest rank plebed. So in that previous example, those lines that I drew up.